In this video, we're going to be learning about some nuclear radiation concepts and learn about some calculations as well. We're going to hit the basic radiation concepts, talk about the different types of radiation, see what they look like as nuclear equations, discuss what happens during decay, and then do a bit of problem solving. So let's first discuss what a radioactive atom even is. It's something that has an imbalance of forces in the nucleus and causing instability. And once it has an unstable nucleus, it's going to emit some energy and particles and decay in order to help stabilize itself. So let's go ahead and write some of those things down. All right, so with our little mini flowchart here, we have a radioactive atom. It has some imbalance of forces in the nucleus due to its protons and neutrons, and because it's unstable, it's going to decay to reach more stability. And in the process, it's releasing some energy and particles. So let's talk about the different types of radiation. Let's go ahead and start off with alpha decay. Now, with alpha decay, you start off with something called a parent nucleus. And your parent nucleus might be something like uranium-238. So if it's uranium-238, we have a mass of 238 in the top left-hand corner, and then we can go ahead and find the atomic number of uranium. It's at the bottom of the periodic table, and it is 92. Now, our parent nucleus is unstable, and what's going to happen is it's going to eject an alpha particle. And an alpha, here's alpha symbol. An alpha particle has a mass of 4, and it has 2 protons. So with that being said, if it has 2 protons, that would mean that it would have to be a helium atom. So when a helium atom is ejected from a parent nucleus, that would be known as an alpha particle. And then from there, what you can do is you can find what's known as the daughter product. And the daughter product is our new atom after that alpha particle is ejected. So all you have to do is some simple algebra and take a look at the conservation of mass. So the first thing we're going to do is take a look at the mass. So we have a mass of 238 for our original uranium atom. And then on the other side, it has ejected a helium particle with a mass of 4, and then we have some kind of unknown daughter product. So we can do some simple algebra and do 238 minus 4, and that would give us 234 for the mass of our unknown daughter product. Now, we still don't know what element it is, so we have to do a little bit more calculating. We know as far as the protons go, we have 92 total protons on the left, and that's equal to the 2 protons of our alpha particle plus some kind of unknown value over there. Again, some pretty simple algebra, subtract 2 from both sides, and then we'd find out that the number of protons is 90. Now, if the number of protons is 90, then we go ahead and look a little bit to the left of uranium on the periodic table, and then you would see thorium, and then you could go ahead and write TH for the element symbol of thorium. All right, to sum things up for alpha decay, we start off with something called a parent nucleus, and because it's unstable, it ejects an alpha particle, which is always a helium particle with a mass of 4 that has 2 protons. Then we have our remaining daughter product after that helium is ejected, which is always going to be slightly smaller than the original parent nucleus. You do a tiny bit of algebra to find that mass and the atomic number, and then go ahead and hunt down that element on the periodic table to put your symbol, which ours ended up being TH. All right, that does it for alpha, so let's go ahead and check out beta decay. So for beta decay, we are going to start off with our original unstable atoms. Say, for example, we have carbon 14. So we have carbon, mass of 14. It always has an atomic number of 6. Now, this one is similar to alpha in the sense that it's going to eject a particle and then change what kind of element it is. But for this one, when it ejects a beta particle, that is an electron. And the electron has 0 mass and a -1 value for the number of protons because it's basically emitting an electron from a neutron and then turning it into a proton. So this little electron here is known as our beta particle when we're talking about beta decay. Now, just like for the other one, we have to do a tiny bit of math across the top and the bottom. Pretty easy for this one because it's 14 equals 0 across the top. So we know that the mass still remains 14. And then across the bottom, we have 6 equal to -1 plus x. Okay, for that one, we're going to add 1 to both sides, and then that would give us 7 protons total. So because that neutron emitted an electron to become a proton, we have 1 additional proton in the nucleus. So now we have an atomic number of 7, and if we look that up on the periodic table, that would now change it into nitrogen. All right, moving on, we're going to go to gamma decay. So for gamma decay, we might start off with something like helium-3. So helium-3 has a mass of 3, and it always has an atomic number of 2. Now for this one, what happens with gamma decay is it just emits a photon and then it goes to a less excited energy state, but it doesn't actually emit any mass. So for gamma, there's a symbol for gamma and it is massless. So it's actually 0 and 0. So for this one, mathematically, you're really not doing much of anything. You're just still going to have a helium-3 particle. So you're going to have the same exact atom before and after, but it's just emitting some energy, but it's not actually emitting a particle that changes the type of element it is. All right, moving on to our last two, we have electron capture and positron emission. So for electron capture, it is exactly what it might sound like. It's capturing an electron. So say, for example, we have something like carbon 11. So carbon 11, mass of 11. Carbon always has an atomic number of 6. Now for this one, because it's capturing an electron, we have the electron on the left side of our formula. And then after the nucleus absorbs an electron from an inner shell, a proton changes into a neutron. So what happens here is if we do the little mathematical part, we have 11 plus 0 on the left side, and that's going to tell us our mass on the other side, which of course then is 11. And then on the bottom section, we have 6 plus -1 when we're taking a look at our protons, and then that of course would be 5. So that changes our atomic number to 5, and then we would find 5 on the periodic table. And if we found 5 on the periodic table, that would give us boron. So it's kind of similar to beta decay, except instead of having the electron on the right side of the arrow, we have the electron on the left side of the arrow because it's absorbing an electron and converting that proton into a neutron because of its unstable nucleus. All right, moving on to our last one, we have positron emission. All right, now with our positron emission, we might start off with something like a nitrogen 13, so we'll call that N. 13 for the mass, atomic number of 7 always goes along with our nitrogen. And then a positron emission is similar to beta, except it's releasing a positive particle, which is kind of the exact opposite of what an electron is. But it's emitting the positive particle from a proton and converting it into a neutron. So what you're going to do there is, again, if you do the math across the top, we have a mass of 13 on the left, none on the right. So we have a mass of 13 for our daughter product over here. And then we also can work across the bottom. And then we have 7 on the left equal to 1 plus x. Subtract 1 from both sides, and then we have an atomic number of 6. Okay, now with that being said, if we know the protons are 6 and the atomic number is 6, then it definitely has to be carbon. All right, so for each of the different types of nuclear decay, they have some defining characteristics of something that they're releasing or absorbing in each of the different cases. So you can use those defining characteristics to work out some problems. So let's work out a couple problems and see what that looks like. All right, so for our first one, we got magnesium 24 as a product that has undergone beta decay to get that product. So we have magnesium on our product side, that's over here. And we know it has a mass of 24. We can go ahead and hunt down magnesium on the periodic table, and it is number 12. All right, now if it undergoes beta decay, remember a beta particle is when something releases an electron and then converts a neutron into a proton. So we know for sure we're going to have the beta particle on this side is 0, -1, E. And then we just have to do a little bit of math. This one is pretty simple. 0 plus 24 on the right side, which makes it 24 on the left side. And then -1 plus 12 on the right side, which gives us 11. And then the last step we're going to do is find number 11 on the periodic table. And then that is going to give us Na, sodium. So in this case, we just had to do a little bit of math, and we also had to know that a beta particle is a 0, -1 electron on the product side. All right, for number two is basically doing a little bit of algebra to start off with. For this one, we have 238 equals 234 plus blank, and 238 minus 234 is just 4. And then 90 minus 88 on the bottom is 2. So we know that this is a helium particle, which would mean that it's going under alpha decay. So once we have solved for one of our unknown products, then we'd be able to identify which kind of decay it is. If we found out that it was a 0 negative electron, maybe we would find out number 2 is a beta decay, or if the atom was maybe exactly the same, we would find out that it's gamma. Either way, these are a couple little problems where you're typically going to be using a little bit of math, a little bit of algebra for those masses and those protons, and then from there, you're going to want to know some of the defining characteristics of those different types of radiation. So I hope that was helpful to you. Thank you for watching and listening.